Hello everybody, welcome to the first video for section 4.2. Continuing on with our studies of different applications of calculus. And as we're going through this one here, this one's a little bit more theoretical, but for any of you who are looking into studying computer science, or maybe you've wondered how a calculator works, how a calculator calculates things, this section will help us better understand that. Okay, so first thing we're asked to do here is we're given this function f of x equals cubed root of x, and they want us to find the equation of the tangent line at the point x equals -8. Now, if you recall, when we first started studying concepts of calculus, finding tangent lines or equations of tangent lines was kind of our motivation. So recall how we do this is we first start by taking the derivative of our function here. And when we take the derivative for this type of function, the cubed root of x, it's helpful to rewrite it as x to the 1/3. So we can take the derivative there and end up with 1/3 times x to the -2/3 using our power rule. And then we can plug in the point we were given, or the input value we were given. So f prime of -8, do 1/3 times -8 to the -2/3. And if you work that out, you can plug it in your calculator or do the cube root of -8 or 1 over the cube root of -8 squared. Regardless of how you do it, I think you will end up with 1/12. And recall that the way derivatives work, when we evaluate the derivative of a function at a particular point, it gives us the slope of the tangent line at that point. So we know that when x equals -8, the slope of the tangent line is 1/12. Now, how do we use that to find the equation of the tangent line? All right, so we also need a point on the function. So that means we need to take our function here and plug -8 into that. So we'll do f of -8 goes cubed root of -8, which is going to give us -2. So now we have a point, -8, -2. We have a slope, which is 1/12. And now we can use that information to find the equation of our tangent line. So when we do that, recall we'll use, and I'm going to call the function g of x equals mx plus b. We can plug in the information we have, so we know the slope is 1/12. And we need to find the value for b. And so recall that to do that, we need to plug in the other information we have, which is the point here. So I have 1/12 times -8 plus b, and we know we input -8, our output should be -2. We can solve this, and when we do, you end up with b equals -4/3. So therefore we know that the equation of the tangent line at this point would be g of x equals 1/12 x minus 4/3. And there we go. All right. Now you're thinking, great, Cody, this is wonderful. Thanks for this review, but we already knew this. Why are you bringing this up? Well, I want us to look at the graph of the function along with the graph of the tangent line. And I've got that here on Desmos. So you notice here the red function here, as you can see from the left over here, that is our function f of x. I have x to the 1/3, but it's cube root of x. And then the blue function there, that's the tangent line, okay? And I want to zoom in on the point we were just looking at, which was at x equals -8, which looks like that would be right about, so -8 looks like it's right here, so we're looking at a point here. Okay, so I want to zoom in on that. Okay, and I want us to notice, first of all, that in this window I have right now, right, notice that for values close to -8, oops, sorry. For values close to -8 there. The tangent line, which if I can get it to highlight again, there we go. The tangent line seems to almost lay right on top of the function, right? And so what that tells us then is the output values for the tangent line around this point are going to be really close to the output values for the function itself, right? And notice that that's most true for values that are close to -8. If I zoom out, for example, can I look at, say, like x equals 1? Well, notice there, right? So x equals 1 is right here. Notice that the output value for the function is up here while the output value for the tangent line is down here. So those values are really far apart. But again, close to the point where we found the tangent line, so at x equals -8, they're almost the same. So why is that helpful? Well, what that tells us then is that the tangent line, the equation of the tangent line, could be useful for estimating output values of the function for inputs that are close to -8. Now, why would we ever care about that, you ask? Well, as you can imagine, calculating cubes roots of things is quite difficult, right? Unless you have a calculator or maybe some sort of number processing software, right? It's going to be really difficult for you to find the cube root of things like -8.1 or -8.01. However, if we can take one of those numbers and plug them into a linear function like this, the 1/12 x minus 4/3, well, that's a calculation that's a little bit more manageable for us to do, right? Because even though we might have to deal with some nasty fractions or decimals, at least we can make that calculation. Now, the reason I said at the beginning that those of you that are into computer science or have ever understood or wondered how a calculator works, this is what I was referring to. So often calculators also don't take cubed roots of things because that's really difficult to do. So they're instead programmed to take some derivatives, find a tangent line like this, and then use the tangent line to estimate the output values. And they're usually, as you'll see here in a second, quite accurate. So it's okay to use these. Okay. All right, so let's take a look at how this works. So they tell us to use a tangent line to the function at this point, at x equals -8, to estimate the values of the function at x equals -8.1 and x equals -7.9. So recall we found the equation of our tangent line was g of x equals 1/12 x minus 4/3. So I'm going to take each of these values here, so the -8.1, and we're going to plug it into the equation for the tangent line, not the equation for the function. So we'll do 1/12 times -8.1 minus 4/3. Okay, and we can work that out on our calculator. And when we do that, we end up with -2.0083 repeating. And also do the same thing with the -7.9. Okay, so I have 1/12 times -7.9 minus 4/3. Okay, and plug that in the calculator. I get -1.9916 repeating. Okay, and so recall that those are estimations because we used the equations of the tangent line to come up with those. But let's cross-check those with what we would have gotten if we just plug them straight into the function. So I'm going to do f of -8.1 now. So it means I'm going to plug it into my original function, which means I'm going to do the cubed root negative 8.1. And if I plug that in my calculator, I get negative 2.008299. And notice what we've got there is not exactly the same as what the equation in the tangent line gave us, but it's pretty darn close, right? We're only off by like 0.0001 and not even that much, right? So our estimation there was pretty darn close. Similarly, if we do it with negative 7.9, so we take the cubed root of that, we end up with negative 1.99163, which again is not exactly the same as what we got from the equation in the tangent line up here, but it's really, really close. Okay, we're off by like 0.00003. So very, very close. So we see that these estimations with the tangent line are quite accurate. Now, I want to reiterate again that this only works for values close to the point where we found the tangent line. So again, let's plug in, say, 1 now. So I'm going to do g of 1. So plug that into the equation of my tangent line. So I'd have 1/12 times 1 minus 4/3. That gives us negative 1.25. But if I do f of 1, so I plug it into the original function when we're doing the cubed root of 1, which is just 1. And notice that's nowhere close to what the equation in the tangent line gave us, right? So that's an example of how this doesn't work for values that are far away from the point we used to find the tangent line. Okay? All right. So let's, what we just did is called a linearization of a function, which again is something that's really common, commonly used in computer programming, and some calculators use this as well. So, and we're going to come up with a kind of a more general format for this. So the setup here, you'll see in the picture. So we have a function we're calling f of x, and that's the blue line there. We have a point on that function, so the input value is a, the output value is represented by f of a. So in this case, like a would be our negative 8 from the previous problem, f of a would be the negative 2, what we got from plugging negative 8 into the function. And then they're calling y equals L of x. I'm going to focus on this L of x. That's going to be the equation of our tangent line. Okay? And recall that to find that equation, that tangent line, first thing we did was take the derivative of the function. So we found f prime of x. But then we evaluated that at the input value we were interested in, right? So really what we found was f prime of a. And recall that that gives us the slope of our tangent line, right? Oh my goodness, I cannot write right now. There we go. So that's our slope of our tangent line. And then we would use that along with the point we have, which in this case is a comma f of a, to find the equation of our tangent line. So remember, we were just using g of x equals mx plus b. Fill in the information we have. Well, we know that the slope we're representing by f prime of a. X is our input value, so that's a. And then we need to solve for b, and the output there is f of a. Okay. And so what we can do then is solve for the value of b here. And so when we do that, we'll end up with, you can subtract over the f prime of a times a on both sides. And so when we do that, we'll end up with b, move this over here. So b is going to equal f of a minus f prime of a times a. right? So now we have the value for b here. Let's again have our value for m, so we can plug those in up here to write the equation of the tangent line. So I'm going to erase again. And sorry, erase something there I didn't mean to. Okay, so let's plug this information in. I also put the wrong thing there. That's supposed to be a g. Okay, so we're going to have g of x equals the slope, which is f prime of a times x, plus the value for b, which is f of a minus f prime of a times a. And then we're going to do some rearranging here. So first of all, notice that both of these terms here, that negative f prime of a times a and the f prime of a x, both have an f prime in them. So I could group those together and factor out that f prime of a. And so when we do that, we'll end up with f prime of a times the stuff that's left over, x minus a. So that's coming from the x here, and then the minus a here. Darn it. Okay, and then we still have the plus f of a here. Okay, and what this gives us is a general form for the linearization, or the equation of the tangent line for a function. Okay, if we're trying to do these estimations based on this. All right, so let's use this on a problem. So here we're given this function h of x equals square root of x plus 3. And we want to find the linearization at x equals 1. So we're going to use that linearization. And sorry, I forgot one thing. I called the line g of x on the last slide. But as you recall, here they used the label L of x. So that's what I should have used. I apologize. So here, what we want to do is to find the linearization, we're going to use this function, or this formula, L of x equals f prime of a times x minus a plus f of a. So you can see there's some things we have to identify here and find. So we need to find f prime of a, figure out what a is, and then find f of a. Well, a is just the point we're finding the tangent line in, so that'd be x equals 1, or just 1. To find f of a, that's going to be, we plug in 1 into our function here. So in fact, we can do that. So we have h of 1 equals square root of 1 plus 3 equals square root of 4. So that's 2, right? And then to find f prime of a, we have to find the derivative. So let me go down below. I apologize. So to find h prime of x, which if we do that, I'm going to skip a few steps here. That's going to become 1/2 times x plus 3 to the negative 1/2. And then we'll plug in our point to that. So I have 1/2 times 1 plus 3 to the negative 1/2. And that will give us 1/4 if you work that out. Okay, so now we plug in all of this information. So our L of x will be equal to f prime of a, which was 1/4, times x minus the value for a, which was 1, plus f of a, which is 2. And then you can simplify that a bit, because 1/4 can be distributed in here, and then we can combine some like terms. And when we do that, what we will end up with is, once I figure this out, so that will give us L of x equals 1/4 x plus 7/4, if you work that out. Okay, and so that's our linearization, and I know I'm calling it a linearization because that's what this part of what this section is about, but know that that's just the equation of the tangent line to the function h of x at x equals 1. And now they want us to use that to approximate the values for the square root of 3.98 and the square root of 4.05. Now, let's notice, and I'm going to start with the 4.05 here, that those both have roots in them, so they must be related to this function h of x up here somehow, right? Which means we'd have to like plug something into the function there, and we plug it in over here, and then somehow we'd get the square root of 4.05, right? Now let's be very careful. Notice that what I would be plugging into the function here would not be 4.05, right? Because I have to take whatever I plug in and add it to 3. So what would I actually be plugging in here? Looks like I'd plug in 1.05, right? Because if I do 1.05 plus 3, that's going to give me the 4.05. So in order to approximate the value of the square root of 4.05, I need to approximate h of 1.05, which we can approximate by doing L of 1.05, so using what we have from linearization up here. And so that means we plug in our values into our equation of our tangent line there, so do 1/4 times 1.05 plus 7/4. If we do that, we get 2.0125 as an approximation for the square root of 4.05. Okay, so that would be our first answer. All right, so let's do the second one now. Well, it was the first one, but we skipped it. So now we need to find square root of 3.98. And again, we have to think about what would we plug into the function h here to find that. And I believe the answer would not be 3.98, right? What would have to go into here to give us a square root of 3.98? Well, it looks like that answer would be 0.98, right? Because we do 0.98 plus 3, that'll give us 3.98, and here in the function then we'll have square root of 3.98. So we need to approximate h of 0.98, which again we can do by plugging into our function or our linearization there. So do L of 0.98 equals 1/4 times 0.98 plus 7/4. If we work that out, we end up with 1.995. Okay? And so that would be our approximation for square root of 3.98. Now, in both of these cases, you can double check and actually plug in square root of 3.98 and square root of 4.05 into your calculators and see what you get. And hopefully, you will get something very close to the two answers we just found. All right. Well, thank you guys for watching. That's it for now.